The talk I will be giving today is on the topic of durable execution. So probably that's a new term for many of you, since it's a slightly newer upcoming thing, like a new child on the block. And the area in which you can situate it is basically resiliency for microservices. So to explain it in very short, basically what it tries to do is, if you have services in your infrastructure and they are processing, like they are executing functions and they're manipulating state, some variables, etc. When that service crashes, you basically lose all the intermediate progress, so you don't know where exactly in the function you were, and you lose all the other state that you basically have in that service, unless you persist it to a database or do some extra things in your code. And the idea of durable execution is actually making services being able to recover to the point where they were before a crash. So basically, we bring the service back exactly to the point before the crash. So let's have first a bit of context on current ways microservices architectures are structured. This is a very simple pseudocode example. You want to process an order. The first thing you want to do is do the payment, and then you want to deliver it. But if you look at these two lines of code and imagine of how you would make them actually fully resilient in a production use case, it's already not so easy anymore. How do you make sure that when you crash right after the payment, on a retry, you don't do the payment 2 times? Or that you make sure you at least do the payment 1 time and don't deliver something that wasn't paid yet. So already quite quickly you see that you need to start introducing other systems in here. Like you need to start introducing things like, for example, a key value store to store some app state, like for example Redis. You need to have things like message queues for things like async events to make them reliable. Workflow orchestrators to keep track of what was executed and what wasn't executed yet. And the list goes on and on. One final example is, for example, schedulers to have things like durable timers to be able to say, execute this for me in 15 minutes. For example, in an e-commerce application where you want to say, expire the content of my shopping cart in 15 minutes. To make that durable, you already quite quickly need to start implementing all sorts of other solutions and technologies in your stack. And what you end up with is actually still quite a lot of manual retry logic and recovery logic to basically keep the consistency across all those systems. Because they offer point solutions, but you need to still write the glue across those. And in some cases, you still find in production new corner cases popping up that you just didn't think about yet, different ways that things can go wrong. And then the solution often is to just send a voucher to the customer and apologize and hope he doesn't leave you. So what you end up with is like quite a complex architectures often, while the business logic actually is fairly simple. You don't want to do something so complex, but you end up with architectures where almost nobody can keep the overview anymore. What would happen if one thing in there would crash? And even with all those point solutions, there are still many things that are so hard to get right. Things like race conditions, like we have this process order function, for example. What if it gets called 2 times for the same request? How do we deduplicate that? Things like inconsistent state. What if a state update went through, but we weren't aware of that yet, and during our retry we updated it again? All these kind of like interactions between systems that make things just very hard to get them 100% correct. So what if we can basically take another approach to these types of problems? So let's take a leap of thought. What if code execution itself would be durable and would basically be able to recover after failures? So that's actually the idea of durable execution. So in one sentence, basically what it does is it tracks code execution to be able to recover it, to recover a service to the exact point it was before the crash. So when it comes to communication, to state, and to what you were doing, basically. There are different projects popping up in the space of durable execution, different implementations of the same philosophy, let's say. Most of them actually use a log-based approach. I work for the project Restate, so I'll be showing the approach Restate takes. You are free to, of course, check out some other solutions and see how they differ. So the idea of Restate is basically that you have a central server sitting in between your services, and the central server is basically the one which tracks the progress. So what happens is if you have an invocation, like for example an RPC call to a specific function, it gets proxied via the server and then sent to the service. And the service has an SDK embedded in it, and basically what will happen is Restate will open an HTTP2 stream to the service, and will start sending over the request over the open connection. And the service, on the other hand, will start sending notifications of the progress of what it's doing back to Restate. So they basically cooperate to make sure the execution is durable. Let's go a bit more into detail. So imagine you have something like a UI which lets a user submit requests, for example, again, like an order processing flow. You have a request coming in, so what happens? The first thing actually is that Restate basically acknowledges that this request has taken place and that it needs to get executed. So Restate from that point will make sure that that request will run to completion, whatever completion is in that case. And then it will forward the request to the function. So that's just like the normal RPC calls that you use or know. What then happens is the SDK and the function start executing. So as the function is executing, it logs the progress. First it does the payment, it notifies the payment success, that gets added to the log. Then you do the delivery by, for example, calling another delivery service. Also that makes it into the log. And eventually you have like the response of success, which gets proxied back to the caller. So what happens if this crashes somewhere halfway through? Let's take, for example, the case where it crashes right after it does the payment. So our service goes up in flames. What happens is Restate has the log. So what it does is it pushes a retry request to the function, and it attaches the log to the retry request. The function then basically checks what is in the log and skips those steps in the execution of the function. So it sees, okay, the payment was already done, I don't need to do that anymore, so I can continue after that with doing the delivery and then sending back the response. So there are some ways of how you can basically think about this on a higher level, which is basically you have like low latency workflow-like semantics for any function. So workflow orchestrators traditionally are systems you use to execute a set of steps, and you want to make sure that every step is retried until it either succeeds or fails, and based on that you go to the next step and so on. Basically you get this kind of semantics in any function where you would want it. And the idea is that usually workflow orchestrators are more something you would use in like less latency sensitive paths of applications, because they schedule the execution, and sometimes they can like take a second, maybe 2 seconds, and there are things you don't always want in like the latency sensitive paths. So the idea here is that it actually is a bit like low latency workflows. So let's first show a very simple small demo, and then later on I'll show a more complex one so you get a feeling for it. So the example is very simple. It's basically the same one as what I was showing on the slide. So what this looks like is basically we have an HTTP server with our service binded to it. So this is our service implementation. It's an order processor, and now this will listen on port 9086 for connections from Restate. And once that connection has been made, Restate will basically ask it to execute, for example, this function, the process order function. And what will happen then is we will do those 2 steps, first the payment, then the delivery. But now we will wrap them in ctx.run. And what that basically does is if that step gets executed, the result of that execution gets stored in the log, like I showed on the slide previously. And this CTX thing is basically the connection between this function and the SDK, which is in the background. So every time it does something like CTX dot, basically it communicates to the SDK, send this as an event to restate that this got executed, together with, for example, a Boolean response, which is returned from the payment action. So in this little example, the do payment and do delivery functions sometimes crash with a certain probability. So if we call this, we will see probably some retries in the logs. So it should be running already. If we go to the end of the logs and then send a new request, we will just send a request via curl. So the way we do that is basically localhost 8080 is the endpoint of restate in this case. Order processor is the name of my service, and then process order is the name of the function that I'm calling. So it's just an RPC call. There's no like request attached to this because the function doesn't require that, but usually there would, of course, be a request body there. It's okay if we execute that. We see order processed. Let's execute it another time. And then let's see what's happening in our logs. So it's right now 12. So if we have a look here, we see, for example, that the invocation started processing. The first time, actually, the payment was immediately a success, and after that, the delivery started executing. But we see that the second request I did, there the invocation started, but first the payment failed. So we see that the invocation ended because there was a failure, so the invocation crashed, and what then happens is restate triggered a retry. So you see again that the invocation starts, it again fails, and if we go a little bit further, then eventually you see, okay, here it was successful, and then it went on to the delivery. And what you would see if it would be the other way around and the delivery would be the one crashing, then you would see that the payment doesn't get re-executed anymore on the retry requests. And so what do we gain by this is you don't need to write any retry logic there. You don't need to write any recovery logic. Basically, the log is your ground source of truth of what has and hasn't happened. We will make it a bit more complex later on in the talk. So maybe a little intermezzo before we get back to durable execution and the other things you can basically extend it to. This server, what is this thing actually? In the case of Restate, it's a single binary, so that means you don't need to deploy any databases next to it to persist the state. The way it's implemented is it's a Rust service written from the ground up to basically serve the low latency workflow use cases. It has a consensus algorithm to be able to persist what has happened. So together with other nodes, the log is decided on, and once that has been decided, basically that's the new state of the application. It's open source, so you can all freely try it out. We're looking for people to basically provide us feedback and see what would be interesting directions to move in. Right now, there's only a single node version. There's a distributed one coming out pretty soon because we have like a launch event in a few weeks. We're still a fairly new project, only started around 2 years ago. So we're still like adding some of these features every few months. So if you want to follow that, definitely register for that. We'll also be releasing a cloud version for a managed service, but it's pretty simple to self-host it if that's what you want. Okay, back to durable execution. So, okay, well now we have these functions and they execute, and every step that gets executed ends up in the log, but that's really still not enough to build reliable microservices architectures, right? So what is missing? We started with one function, but if you look at microservices, there are always multiple functions, and they communicate with each other in all sorts of ways. For example, request response, where you send a request to another service and wait for the response. Or you want to just send a message and not wait for the response. Or schedule a task maybe for later on. There are many ways in which these functions together communicate. So can we basically take the same approach for this as for the execution and add it to the log? So what happens is basically Restate in that case becomes a bit like an event broker, a bit like a Kafka cluster, for example. It basically proxies events between services. So not just the events that come via curl or via the outside, but also in between services. And when one service calls another service, what happens is Restate makes sure that that nested request executes. Once it's done with that, it just proxies the result back to the calling service. So in that way, you can implement many of the patterns, like, for example, request response, where you do proxy the response back, but also you can send messages like in an async way, for which you would now use a queue. You can just not return the response then to the caller. That's basically what happens then. Or you can, for example, use it for more like callback patterns, where you want to call another service, do some other stuff, and whenever that service is done, it notifies you about that by using a callback. So I will show a few of these examples later on in the more complex example. So right, now we have services calling each other, and we basically have an event broker in the middle that is aware of all the ongoing invocations and requests, and that is aware of whether they're already finished or not and what their result was. So something that actually is very easily obtainable with this is that Restate becomes basically a broker for idempotency as well. So if you attach an idempotency key to your request, because Restate knows whether that invocation was already executed or whether there was already a response, it can either let you latch on to the ongoing one, or it just returns the previous response. So it basically gives you idempotency for those services for free there. All right, so now we have execution, which is durable, and communication between the services. There's one important thing missing, and that's basically state we use throughout our code. Things like, for example, tracking a state machine. Like for the order processing, for example, you want to go through the state machine of new order, paid order, delivered order, or payment failed. If this is just one handler, we could solve it with just the durable execution I talked about, but if you have multiple handlers basically operating on the same state, we need something more. Otherwise, you can have multiple handlers changing the same state, and you will still get into issues there. So what happens there is basically you store the state together with the execution and the communication in a single log. And what happens then is if state updates and execution and communication are all in one log, it's very easy to keep your services consistent, because you have exactly a sequential flow of what has executed and what hasn't executed yet. So this basically guarantees you that the state that you get in your function is always up to date with where code execution is at that point in time. So the way that works is when you have a request, Restate basically attaches the state to the request and then forwards that request together with the state to the function. When the function is processing, it's basically just a stateless handler making state changes, and those state changes are just like the other things I showed, just events to Restate which end up in a log. But what about multiple handlers then mutating this state? So what happens there is you basically need to make sure that you have isolation or concurrency for the state. So at most one handler can be changing state for a specific key. And if you think about this in some way, that's actually making the objects that you have in your code durable. So if we take that a bit further, imagine you have something like a driver service and you have a location in there, and that location regularly gets updated. And sometimes you want to ask like, hey, what's the location of my driver? What would happen then is basically you would have the state, the location stored in Restate as a key value pair. And every time this update location function gets called, it has the previous location attached to it, it updates it, that update gets transferred back to Restate, and the next time you call it, it's again going back and forth that way. So whenever get calls is called, it basically returns the latest location at all times. So if you have execution and state in the same log, in some way you can see that as like an object which permanently lives in restate. And your services itself are fully stateless. So how do you then invoke a driver? Like how are those things isolated? So if you have a class and you have, let's say, the different drivers of this specific driver service, then you can call, for example, one specific driver by specifying the key. And the key, in that case, can either be added to the URL by, for example, saying localhost driver service, driver Harry, and then get his location. Or in the case where you, for example, want to connect it to Kafka, it would be your Kafka key. So this basically gives us a single log across those things, which makes it easier to get to a state where we have resiliency and consistency together across the different aspects of microservices. So for execution, it's within a handler. For RPC, it's across services, processes, and time. And for state, it's basically across the handler executions within one service. Okay, enough talking. Let's show again some code. This is a more complex example. It's basically an e-commerce backend. So imagine a fast food chain which lets you order pizzas and burgers via a UI. You select what you want to eat, and that invokes the order workflow here. And that order workflow does the casual things, triggering a payment, then asking the restaurant to prepare the food, then asking a delivery service to do the delivery, etc. And there is a second part, which is basically the delivery part. So there are the drivers for the restaurant, there is like the managing of the delivery, and those ones get updated over Kafka. So there's a Kafka topic, the drivers have basically like a mobile phone. That mobile phone publishes regular updates on Kafka, and those updates will then be sent into the system. So let's first show the order workflow. So it's again the same structure. We have a service defined with a function inside it. That function gets called. In this case, it gets the context supplied and the request. So in this case, the request is the order. And then it starts executing the code. So the first thing here is an example of a payment. So what happens is we first want to generate a unique identifier for the payment to make sure that we then don't do the payment 2 times. So basically a stable idempotency token that is the same across retries. Because many payment providers, such as, for example, Stripe, allow you to attach an idempotency token to your payment request, and they then duplicate, based on that unique identifier, whether this is a new payment or not. So that's pretty easy if you have a log, because you can just store the idempotency token in the log, and once it has made it there, it will be the same across restarts and retries. And then if you call a payment provider, you supply that token, and that token will here always be the same. So let's show an example of that. This thing also should crash sometimes. So if I go to my UI and I order a pepperoni pizza, then that should lead to a invocation in my service here. Is it the right one? It's 22:12. So here is the start of the invocation. And then it says, okay, I'll try to execute this payment with token 851, etc. Then we see the payment failed for this token. So again, a bit like the previous example I showed, you see the retry taking place. Then again, it will try to do the payment, and you see that the token is the same. It's still the 851 token. And now it succeeded, and then you can continue with the rest of the workflow because that payment then took place. All right, maybe like a few other things. I didn't talk about timers yet, but if you have a system which basically keeps track of everything that is ongoing, it can also keep track of timers, because if whether the service is running or not doesn't matter. It can keep track of things it needs to execute in the future. So you can do things like calling another service after a delay, for example, after a month or after a week, or sleeping for an arbitrary amount of time. And basically what happens is Restate will be the one tracking the timer. When it sees the timer has expired, it basically invokes that handler or service again and says, this is the log, and by the way, that sleep has now been completed, so you can continue right after it. So here in the example, what we're doing is, for example, allowing a customer to order at a later point in time. So what happens is we supply a delay and then let this function just sleep for that amount of time. So we can show in the log what that looks like. If we, for example, order a pizza in 15 seconds, what happens then is if I, with the CLI, have a look at the invocations that are now happening. Whoa. Did I press checkout? No, okay. Then if we look at the invocations that happened, we see here the invocation. So if we then ask it to describe this invocation for us, then we see the current log. So this is the invocation that's now running. We see here the invocation progress. So what has happened is it has sent a message, then did the payment, which is those two ctx.run calls. And right now it's sleeping. So it still had 4 seconds left at this point. So if I now re-execute this, we see that the log has become longer because it's further down in the flow of handling the delivery. So if that service would now fail somewhere across the time, basically this log would get sent over. So the CLI allows you to basically like have a bit of a look at what is in the log and do debugging when an invocation is stuck, for example. You can see where it is in the flow or which service it's waiting on, etc. Okay, so that's the timer side of things, but I didn't talk yet about communication. So a few communication patterns that are quite cool or interesting. For example, the durable callbacks. Imagine we want to call the restaurant and ask it to start the preparation. That can take like an arbitrary amount of time. For a lasagna, it can be an hour. For a sandwich, 5 minutes. What we do in that case is, for example, supply a callback and ask the restaurant to just tell us when it's done with that. So what happens here is basically the awakeable creates an ID and a future or a promise for the more JavaScript-like languages. And what we can then do is when we call the restaurant, we supply that ID to our request, and the restaurant can then later on tell us when it's ready. And what we do is we basically wait on the future to be resolved. So when the restaurant supplies the ID back, this line will unblock and will continue with executing. And again, if this takes like a long amount of time, that doesn't matter. It can be like a human in the loop who needs to review something for a week. If that crashes anywhere, that just gets brought back to this exact point. The final example of communication is sending messages, so basically like a message queue. When you write your code and you write these services, when you compile this, it generates clients out of the box. So you can basically use generated clients to call other services. If you add send to the call, then it becomes a one-way thing, like you don't wait for the response. If you don't add that, it becomes a request response call. So what we do here is basically call the delivery manager in a one-way call and then ask it to execute the start function. So this is the name of the function in that other service. So that's a bit the order flow. Let's maybe have a short look at a slightly different example. So an example I already showed a little bit in the slide, like the implementation of the delivery services and the driver. So you could imagine the driver as almost like a digital twin of the real driver which is out there. The driver almost lives within Restate with a status of whether he's working at the moment or not, the delivery he's currently doing, and his location. And what we can then do is we have different functions which we can basically let mutate that state. And those functions, at all times, only one will be executed because we have that guaranteed single concurrency for execution of those handlers. So an example of what we can do then is, for example, this one, handle driver location update event. So this is the one which reads from Kafka. So for those of you who have implemented like Kafka consumers or stream processing apps in the past, usually what you would need to do is connect to Kafka, then poll and ask it to give you the latest batch of messages, then loop through the batch, process all of them, and then commit the offsets to say, okay, this was processed, that was processed, that was processed. But in this case, basically that work gets pulled out because Restate is the one reading from Kafka, and it just pushes events to your functions. So the handler implementation for RPC becomes the same as for Kafka. This function can be called via RPC or via Kafka. So we get here a location that's basically the body, the Kafka body. We then store it in the state, and if the driver has a delivery going on, we also let the delivery service know that the driver is a bit closer to his goal. So that's an example of how you can basically hook up functions also to Kafka topics and combine RPC and Kafka within one service. Let's maybe also have a look at where our driver is currently located. So something else you can do with the CLI is basically query the state. So our driver was driving around and had like a location. So if we then do restate, get the driver A state, what we get back is basically his current location and his current status. So he's waiting for work, and this is basically what is now stored in that key value state store inside Restate. So whenever there is now a new invocation for driver A, this will get attached to the invocation and get sent to that function. All right. So a little recap of what we actually showed. First thing maybe to note is that so we implemented the durable function, but you didn't see any retry logic or partial progress recovery logic, right? Like if we go back, for example, to the order workflow, if you read through it, it reads like super sequential code, like do the payment, schedule the preparation, sleep, etc. Nowhere you see like recover the progress or do retries if this didn't take place. You can basically all of that just lives inside Restate as a log. Some other things we implemented are like timers without using things like workflow orchestrator, schedulers, or cron jobs. The communication that I talked about, like the messages and the response calls without having to deduplicate them or deploy message queues. The idempotency, because you restate, make sure everything gets executed only one time. And the key value state, which is basically consistent and has concurrency guards built in. All right, so if we now take a little detour for those of you who use AWS Lambda in some projects. AWS Lambda is a function as a service platform which lets you execute functions as you go. It's basically you pay for the execution time that you use. When you have an invocation coming in, the function spins up, it executes, and then it suspends again when it's done. So that actually works super well with the durable execution paradigm, because if services can basically almost be stateless, and they get the state and the request and what they need to execute delivered to them, then they can basically just start executing that. Whenever they get to a point where they cannot continue anymore, where they wait for a timer to fire or where they wait for another service to respond, they can just suspend and let Restate or the durable execution engine basically do the waiting. So you save on compute time there, because you can basically let your Lambda function call another Lambda function. It suspends. You can see that almost as like throwing a fake error to just let the Lambda function go away. And then when it's able to progress, it will get invoked again, and it will continue right where it left off, because a service can recover at any time. So that's for the function as a service use case, is quite an interesting one. All right, then maybe a little overview of some use cases for durable execution. Some of the things we already talked about, like workflows as code, so things like a checkout flow or any function that you basically want to have like durable guarantees of the steps that it's executing. Another example, there's, for example, infrastructure provisioning, where you have a lot of retries. Sometimes you need to wait for a resource to be up, try again. That kind of like flows with a lot of external dependencies, and a lot of timeouts are pretty good for it. Or more flexible things like workflow interpreters, where you want to, for example, translate a request into a flexible flow that you want to execute. Or sagas, where you want to roll back, you can like register a rollback step. You just basically put a try catch around a block of code, and in the catch you define what you want to get executed after that, if it fails. The example I showed is also a bit like microservices orchestration. You have functions calling other functions, different services interacting, but resilient, consistent, and scalable. Some examples there, for example, updating one database, then sending a message to a queue, then updating another database, sending an email. So like these steps of interactions with external systems that all need to stay in sync at all times. Or state machines, like this kind of things. Then the function I showed, which was reading from Kafka, is like an example of like a lightweight event handler. So what that lets you do is basically trigger workflows from Kafka, which execute arbitrary event flow. So if some of you, for example, have worked with tools like stream processing, like for example Flink in the past, usually the approach that is taken there is that you have like a DAG, so basically a static flow, and all events get pushed through it. Here we basically take a different approach where there is no DAG. The DAG gets built up by the log basically as the code executes. So every execution, every event can follow a different flow. Also things like interacting with databases, if you look at Kafka applications, those kind of the more transactional type of use cases which are not so easy to implement with the more analytical focused tools like, for example, Flink. And then finally, scheduling of async tasks, background tasks, like for example, clean up in 15 seconds or retry later. All right, so a little recap. Basically, what I talked about or showed is first durable execution, so functions and services that do retries, recovery, and idempotency. And then we extended that to communication and futures in general, which lets us basically have fault-tolerant communication across services, processes, and time. And then finally, the state part and the concurrency to be able to have that together with the other aspects. So that gives you actually some kind of durable distributed versions of everyday building blocks. That's some way to see it. All right, that was basically what I wanted to show you today. If you want to check out the project we are working on, then feel free. That QR code brings you to the docs. In a few weeks, we have a bigger launch. We started a few years ago, but this will be the biggest launch yet. So if you want to follow what we're doing or try it out, we're super curious to hear any feedback you have. So thank you for listening.